everyone, I'm Dr. Rizwana, working as Professor of Physics in Institute of Aeronautical Engineering. Today we are going to discuss about very important equation associated with dielectric materials. In my previous videos, I have discussed a lot about dielectric materials, and then also we have seen different like these dielectric materials. They are known for their very important property of getting polarized once we apply external electric field. And also in my previous videos, we have discussed about different types of polarization, and we have discussed different terms related to dielectric materials. So today in this video, I'm going to discuss about Clausius-Mosotti equation. So there is one important expression related to dielectric material, and that expression, it is in terms of two important factors. Okay, one factor, it is related to macroscopic quantity, and other one is related to microscopic quantity. So here we talk about dielectric constant, which comes under macroscopic property, and then other parameter is polarizability, which talks about microscopic property. And the relation given in between this dielectric constant and polarizability is nothing but Clausius-Mosotti equation. And this Clausius-Mosotti equation has got a very high significance that also we are going to discuss today. So we'll try to get this very important equation, which is relating microscopic and microscopic properties related to dielectric material. But before talking about this Clausius-Mosotti equation, just will quickly try to recollect some of the definitions related to dielectric material. So when we talk about this dielectric material, if we take dielectric material, so when we talk about this dielectric material, first property related to dielectric material is electric polarization. We know that it is, of course, as we know that dielectrics generally they are insulators, right? So dielectrics, they are generally insulators. They don't have any free electrons, but when we apply electric field to dielectric materials, they have this property of getting polarized. Now, what is the process of polarization? Just quickly we'll try to recollect this. Already I have explained it in my previous videos. So in order to apply electric field to a dielectric material, what we'll do, we'll keep our dielectric material in between the two capacitor plates, and then we are going to apply our electric field E. Okay, so in this direction I have applied electric field. Once I apply electric field to this dielectric material by keeping it in between two capacitor plates, first thing is, first we have charges forming on the capacitor plates. So there are storage of charges on the capacitor plates, and as you can see, this left side plate, because it is connected to positive terminal, so that's why this plate, it will become positively charged. Whereas if I take this particular plate, right plate, if we take this one, because it is connected to negative terminal, so this is negatively charged, right? So first we have storage of charges on the capacitor plates. Then after that, what we are going to observe here is, I have my dielectric material, and this dielectric material, it consists of atoms or molecules. Okay, and this dielectric material, it can be monoatomic material or it can be polyatomic material. So what is it is made up of monoatomic molecules or polyatomic molecules. Monoatomic means each molecule, it is made up of same type of atoms, and whereas polyatomic means each molecule, it is made up of different types of atoms, and depending upon what type of molecule is there here, what we are going to observe here is, there is separation of positive and negative charges, because this left side plate, it is positively charged. So this if I take each molecule, suppose I have taken hydrogen chloride, and hydrogen chloride, I have HNCl. We know that this hydrogen and chloride, they'll come together and they'll form bond by sharing a single pair of electrons. But this chlorine, because it is highly electric, it will try to pull this pair of electrons towards it. So this chlorine atom, it will become negative end, and then hydrogen atom, it will become positive end. So what you're going to observe here is, this negative end of diode, it will move to which direction? It will try to come in this direction, because of attraction towards the positively polarized plate, right? Whereas this positive end of hydrogen chloride, where it will move towards the negatively charged capacitor plate. So all the positive charges, they will come here, And this separation of charges, where we have equal and opposite charges separated by a small distance, or where there is formation of electric dipole, then this process it is called as polarization. So what is electric polarization? It is the process of separation of positive and negative charges on application of external electric field to a dielectric material. And in which direction positive ions will move? Generally positive charges, they move in the direction same as electric field, and negative charges in the direction opposite to the field. And this phenomena it is called as electric polarization. Then after that there are some more terms related to dielectric materials. Coming to second one, second term it is called as polarizability. So second term it is called as polarizability, and generally it is denoted by notation alpha. So this polarizability it is denoted by alpha, and generally what exactly is happening when we have applied external electric field. So generally what will happen when we apply external electric field? We have separation of charges. And once, of course, we know what is electric dipole. In electric dipole, we have two equal and opposite charges separated by a small distance. And when we have such electric dipole, then there is some dipole moment associated with it. And how the dipole moment is given? It is given as product of charge into distance between the two charges. So, and this magnetic moment developed, it is called as induced magnetic moment. Why it is called induced magnetic moment? Because here separation of charges is taking place on application of external field, and this external field it is exerting force on these charges to get separated. So that's why it is called as induced magnetic moment. And this induced magnetic moment, it is proportional to strength of electric field. Okay, so it is proportional to strength of electric field. If your applied electric field is weak, then there are only few dipoles. Okay, and whereas strength of electric field is very strong, then all the molecules of this dielectric material, they will be in the state of dipole, and you will have this is electric movement, sorry. So this is induced dipole moment, sorry. This is electric dipole moment, not magnetic moment, electric dipole moment. And here, as you can see here, of course, how much dipole moment is there, it depends upon strength of electric field. And if we try to take out this proportionality sign, this is proportionality sign, we are introducing one constant which is alpha. And this alpha is nothing but polarizability. And if I take this polarizability alpha, simply it is defined as ratio of induced dipole moment to the applied electric field. So what is our polarizability? It is defined as induced dipole moment per electric field applied. So this is about the polarizability. Then coming to next term related to dielectric material. So next term is dielectric constant, and there is one more name to dielectric constant. It is also called as relative permittivity. So it is called as relative permittivity, and generally it is denoted as epsilon r. Actually epsilon, it defines permittivity. So what is permittivity? Permittivity is extent to which magnetic dipoles are formed, or it indicates easily polarizable nature of a dielectric material. And coming to this dielectric constant, is defined as a ratio of permittivity of medium to the permittivity of free space. Now talking about permittivity of free space, its value is 8.854 into 10 to the power of minus 12 farads. And of course, we have permittivity. This epsilon will be different for different materials. Some dielectrics are easily polarizable, whereas some more dielectrics have to apply very strong field in order to get them polarized. Okay, so this epsilon value it is going to change, and accordingly epsilon r value is also going to change. This is about the dielectric constant. Then coming to next term, we have polarization vector. Fourth term is polarization vector. So how we are going to define this polarization vector? Generally it is given by P with the arrow on the top, and this polarization vector, again here also the same concept. Here it is taken to be proportional to electric field strength, and generally first definition for polarization vector is it is defined as induced charges per unit area of dielectric Q dash, it defines induced charges, where we have separation of charges because of applied or under the influence of applied electric field, or it is called as induced dipole moment per unit volume of dielectric. And there is one more definition for polarization vector. It is taken as N mu. What is N here? N is how many number of atoms or molecules present per unit volume of the dielectric, into M is induced dipole moment. So this is the formula for polarization vector. Then we have next one more term. The term, it is called as electric susceptibility. So next term we have electric susceptibility, right? And this electric susceptibility, it is given by chi, and this electric susceptibility, it's a ratio which is given by it's a ratio of polarization vector to the electric field applied. So this is the definition for susceptibility. Okay, and then we have one more term. Okay, and the term, it is called as electric flux density, or it is called as electric flux density, or it is also called as electric displacement. So it is called as electric flux density, or simply it is called as electric displacement. So it is called as electric displacement, and it is given by notation D. Okay, and actually we can say that this electric flux density, so suppose I have a point charge. Okay, let us say that I have one point charge plus Q, and I am trying to measure, okay, so electric flux density at a distance r from this point charge. Suppose I have selected one point A. At this point A, I want to know what is the electric flux density because of this point charge, which is at a distance r. Then in that case, this electric flux density, it is given as charge by 4 pi r square, surface area, which is 4 pi r square. So charge per surface area is electric flux density. So here, by taking that electric flux density formula, and when we talk about this electric flux density, usually it is taken as of course D is equal to epsilon E. Okay, and it is also defined in terms of polarization vector. So as you can see here, next is we are trying to get, before just trying to derive Clausius Mosotti equation. So first thing is we should try to get a very important relation between electric susceptibility chi and dielectric constant epsilon r associated with the dielectric material. Now already we have defined what is electric susceptibility and what is dielectric constant. So before trying to get relation between them, just now I have explained about this electric flux density D. Okay, and we are saying that this electric flux density D, it has same units as polarization vector. So we know that this polarization, it measures additional flux density arising from the presence of the material as compared to free space. So it has same units as D, and this electric flux density, how it is given? It is given as so this electric flux density D, this is the formula for D, right? And it is also given as epsilon E. So as I told you, D electric flux density, it is defined as if I take charge, if I take a point charge and if I try to measure what is the flux at one particular point, which is at the distance r, then flux density, it is taken as magnitude of charge divided by surface area, or because if I assume this r at a distance, of course, if it makes one circle, then what is the surface area of that circle? It is taken as 4 pi r square. So, but when we talk about our electric field E, so E electric field, it is given as 4 pi epsilon r square. So, as you can see here, so it is given as D by epsilon, because this whole term will represent our D. So, if I remove this one, if I consider only this term, so if I consider only this term, it is nothing but our D. So it is D by epsilon. So from this we have a D as epsilon E. And also this D because polarization, it measures additional flux density, and it just compared to free space, so it has same unit as P. So that's why what is the relation between D and P? This is very important relation, epsilon naught E plus E. We have to remember this relation. Now from this relation, we'll try to get of course, a very important equation, which is relating electric flux density and dielectric constant. Now, as we have seen that D, it is defined as epsilon E, and it is also defined as epsilon naught E plus P. And here P is our polarization vector, epsilon naught is permittivity of free space, and epsilon is permittivity of our dielectric material. And of course, E is the strength of electric field. And if I consider these two relations, this epsilon, I can write it as epsilon naught epsilon R E, which is equal to epsilon naught E plus P. And how I got this relation? We know that relative permittivity, which is also called as dielectric constant, it is the ratio of permittivity of the medium to the permittivity of free space. So from this, what is permittivity of medium? It is simply product of permittivity of free space into relative permeability. Now what we are going to do, just keeping P as it is, we are taking this epsilon naught E onto the other side. So this will become epsilon naught epsilon R E minus epsilon naught E. So if I take out common term outside, so epsilon naught E is epsilon R minus 1. Now if I take this epsilon naught E onto the other side, then we have P by epsilon naught E is equal to epsilon R minus 1. But what exactly is this? This is the definition for susceptibility. So chi is equal to epsilon R minus 1. This is very important relation. Now in deriving expression for Clausius Mosotti equation, I am going to make use of this relation. Okay, so we are going to make use of this relation in order to get expression for Clausius Mosotti equation. And as you can see in this relation, we are trying to connect polarization vector to dielectric constant. And by taking this expression relating polarization vector to dielectric constant, I'll try to get, actually this polarization vector, it's a microscopic quantity, and even epsilon R is also microscopic quantity. Now, as I told you, what is our Clausius-Mosotti equation? It gives relation between microscopic and macroscopic. So, by taking this help of this relation, we'll try to get relation between epsilon R, which is macroscopic, and then polarizability, which is microscopic. So, just proceeding in order to derive expression. Okay, for Clausius, of course, it is because this equation, it was done by two scientists, Clausius and Mosotti. After they named this relation, it is called as Clausius-Mosotti equation. And first of all, when we talk about this equation, we say that this equation makes relation between microscopic and macroscopic quantity. So here, microscopic, and of course, not, polarizability. Polarization vector is macro. But here we are trying to get relation between polarizability, which is denoted by alpha, and then dielectric constant, which is denoted by epsilon R. So for that, first we are going to start by taking formula for polarization vector. So all this I am going to do it here again. Okay, of course it is given in the slide. So first I am going to take expression for polarization vector. So first what we are going to do, we are going to take expression for polarization vector. And how we have defined polarization vector? We have defined polarization vector as induced charges per unit area or induced dipole moment per unit volume. And if there are n number of atoms or molecules per unit volume of dielectric, then P, it is taken as n mu. So I'm making use of this formula here. So if I take this polarization vector P, simply we are writing it as P, it is taken as n mu. And here, of course, as I told you, n is the number of atoms or molecules per unit volume of the dielectric. Now, what is mu? Mu is our induced dipole moment. So if we take induced dipole moment, we know that this induced dipole moment mu, which is expressed by mu, it is proportional to strength of electric field. And if we remove this proportionality sign, then mu, it is taken as alpha E, where alpha is polarizability. So where our alpha is polarizability. So here alpha is polarizability. Right? Now, what we are going to do here is, so here instead of E, because already in my video I have a derived expression for local field or internal field, because here what exactly we are doing, we are trying to get relation between microscopic and macroscopic. So we have derived one expression for internal field or local field inside the dielectric material. So internal field or local field, how we have defined this internal field, it is defined as combination of macroscopic fields. So macroscopic electric fields. So if we talk about those macroscopic fields, so macroscopic fields plus microscopic fields. So here we have microscopic fields, right? So and this internal field, of course, this macroscopic fields, they are because of externally applied electric field. So this is because of applied electric field, whereas microscopic field, it is because of the dipoles. So this is because of dipole formation within the material. And what is the expression we got for local field? So this local field or internal field, which is denoted by EI. So this we got it as E plus P by 3 epsilon naught. This is the expression for local field. So that's why what we are going to do now in this formula, suppose if this is equation 1 and if this is equation 2. So in place of E, because we are trying to get relation between micro and macro, so that's why instead of just electric field, I'll take internal or local field, because internal or local field is combination of macroscopic fields and microscopic fields. Okay, so microscopic fields, as I told you, because of external field applied, and in this comes charges developing on capacitor plates and induced charges on the plane surfaces of dielectric. Whereas when we talk about microscopic fields, as we know that we'll assume one sphere inside the dielectric material around the point of consideration, and this sphere dimension is very very small, and induced charges developing on that imagined sphere plus electric field due to dipoles inside the sphere, they'll come under microscopic fields. And this internal field, generally it is greater than applied electric field. Why? Because as you can see, EI, it is equal to E plus P by 3 epsilon naught. Okay, so what I'm going to do, the second equation, instead of just writing mu is equal to alpha E, I'll write it as mu is equal to alpha EI, where EI is our local field or internal field. So we know formula for local field or internal field, it is given as alpha is equal to E plus P by 3 epsilon naught. Okay, and this particular formula of mu, I'm going to substitute in this equation. So what we are going to do, we are going to substitute this value in this equation 1. Suppose if I take this as equation 3, so we are going to substitute equation 3 in equation 1. So next step is, we are going to substitute. So substituting equation 3 in equation 1. So if we do it, then what is our polarization vector P? Then this polarization vector P, which is n mu, right? From equation 3, what is the value of mu? Mu is, of course, n alpha into E plus P by 3 epsilon naught. Now next, what I'm going to do, I'm going to simplify this equation. I'm going to, as you can see in brackets, we have two terms. Now those two terms, they are multiplied with this n alpha. Then we'll have n alpha E plus n alpha P by 3 epsilon naught, and here of course we have our P. Okay, just for the time being we are removing that arrow, but P is our polarization vector. Then after this particular second term on right hand side we are bringing to the side. So we end up having it as P minus n alpha P by 3 epsilon naught is equal to n alpha E. Now what is common factor on the right hand side? We have common factor P. So this can be written as 1 minus n alpha by 3 epsilon naught is equal to n alpha E. right? Now from this, what is the formula of polarization vector I'm getting? I'm getting it as n alpha e by 1 minus n alpha by 3 epsilon naught. So let us take this as equation 4, right? So what we have done here, so as you can see here, first I have taken this expression for polarization vector, which is given as n mu, right? Then after that, we try to explain induced dipole moment in terms of polarizability and also in terms of local field. And this internal field or local field, it is given as E plus P 3 epsilon naught, where E is applied electric field, alpha is polarizability. And if we substitute this value of induced dipole moment in our polarization, and after rearranging the terms, we end up having formula for polarization as n alpha e by 1 minus n alpha by 3 epsilon naught. Now moving further, so we have come to this step. This we have taken it as equation 4. So this is our equation 4. So we are to this point where we got our polarization vector as n alpha e divided by 1 minus n alpha by 3 epsilon naught. So this is our equation 4. Now, what I'm going to do, as I told you in Clausius Mosotti equation, we are going to make use of this relation. So this relation is very, very important. So this is the relation. See, we have introduced polarizability here, right? And here we have polarizability and of course polarization vector. Now I need to introduce our dielectric constant. So for that, what I'm doing, I'm using relation for polarization vector, which is given in terms of dielectric constant epsilon r. So if I take help of this equation, so how this equation is defined, this polarization vector, it is given as epsilon naught E into epsilon r minus 1. So this is our fifth equation, right? And then what we are going to do, we are going to substitute equation 5 in equation 4. So we are going to substitute equation 5 in equation 4, right? So if we do it, then what we are going to observe here is, so on left hand side of this equation 4, we have this equation 5. So this equation 4, it will become epsilon naught E into epsilon r minus 1 is equal to n alpha E by 1 minus n alpha by 3 epsilon naught. Right? Now, after this, what we are going to do, now I'm going to take this 1 minus n alpha by 3 epsilon naught onto the other side. Okay. So here, as you can see here, of course, we have come to this particular relation. Now I'll take this term on the other side. This will be taken on the other side, and this term, it is brought here. So just exchanging the terms. So as you can see here, in this particular relation, just we are exchanging the terms. This term, it is brought to the denominator, and whereas this denominator term on the right side, it is taken onto the left side. Then what happens to our expression? So here I'll have 1 minus n alpha by 3 epsilon naught. So it is equal to n alpha. So n alpha e by epsilon naught e into epsilon r minus 1. This is what we are going to do. Now I'm going to put 1 as it is, and then this minus n alpha by 3 epsilon naught I'm going to take on the other side. So all this is simplification part, no logic here. Just in order to get simplified equation between our polarizability and dielectric constant, just we are trying to rearrange our terms. So just I'm taking this minus n alpha by 3 epsilon naught onto the other side. So this will become plus n alpha by 3 epsilon naught. Now as you can see, what are the common terms? In the second term, we have n alpha by 3 epsilon naught, and here also have n alpha by epsilon naught. So here, now I'm going to take those terms. So I'm going to write this equation again in our next slide. So what we got? N alpha. So here we have n alpha E by epsilon naught E into epsilon R minus 1 plus n alpha by 3 epsilon naught, right? And what is the equation number? We can give this equation as 5. Then after that, taking out common terms outside. So what we have here, I'll try to take n alpha by 3 epsilon naught common. Then what happens to our first term on right hand side? So what is left now? Because we don't have any 3 in the denominator, so obviously we have to add a 3 in the numerator. So here we have 3 by, right? So here 3 by epsilon r minus 1, right? And one more thing here, of course, once we got this here, actually we have to cancel E and E. So there won't be any E here. So when we are comparing these two equations, when we compare equation 4 and equation 5, we know that we have E on the other side. So this E will get cancelled. So when this E gets cancelled, then there won't be any E in the numerator and denominator. So here E will be missing. So in the numerator as well as denominator. So our expression here does not have any E here. So this is n alpha by epsilon naught epsilon r minus 1 plus n alpha by 3 epsilon naught. So here, because we have taken 3 outside, so in the numerator we have 3 here, 3 divided by what is left in the denominator, epsilon r minus 1 plus, of course, because we have taken this term as it is outside, so this will become plus 1, right? So now, so this 1 is equal to n alpha by 3 epsilon naught. Now we are going to take LCM. So in the denominator we have epsilon r minus 1 divided by, so this will be 3 plus, here we have 3. So 3 plus, and here epsilon r minus 1, right? And if we simplify it, 1 is equal to n alpha by 3 epsilon naught into, now here I have 3 minus 1, so it will become epsilon r plus 2 by epsilon r minus 1. This is what we are going to do. Now I am taking this term onto the other side. So if we take this term onto the other side, then numerator and denominator, they'll get interchanged. So here, now we end up having our expression as epsilon r minus 1 by epsilon r plus 2 is equal to n alpha by 3 epsilon naught. So this is one form of our Clausius-Mosotti equation. Very important relation. So what is the significance of Clausius-Mosotti equation? So like this particular formula we can use even in numericals also. So if we are given value of polarizability, we can find value of dielectric constant, or it can be vice versa. So if we are given value of dielectric constant, we can find value of polarizability. So here what exactly is this Clausius-Mosotti equation? It is giving relation between microscopic quantity associated with dielectric material, which is polarizability, to the macroscopic property related to dielectric material, which is nothing but dielectric constant. And how polarizability is defined? It is defined as induced dipole moment per unit electric field applied. And of course, dielectric constant, what is the other name for dielectric constant? It is also called as relative permittivity, and it is taken as ratio of permittivity of medium to the permittivity of free space. And there is one more form of Clausius-Mosotti equation. So we'll try to get that one more form. So once we get this form, we'll try to get one more form of Clausius-Mosotti equation. So for that, we are going to take this derived expression. So if we try to take this expression here, so what is the expression we got for Clausius-Mosotti equation? Epsilon r minus 1 divided by epsilon r plus 2 is equal to n alpha by 3 epsilon naught. So this is the one form of Clausius-Mosotti equation. So this is what we got here. So this is one form of Clausius-Mosotti equation. Now we are trying to get another form of Clausius-Mosotti equation. For that, what I'm doing, I'm multiplying both sides by m by rho. So what I'm doing, I'm multiplying both sides. So multiplying both sides by m by rho. In this m by rho, what is m? M is molecular weight. M is molecular weight, and what is rho? Rho is density of material of dielectric under consideration. So what we are doing? We have taken this Clausius-Mosotti equation, which is relation between polarizability and dielectric constant, and that relation it is multiplied by m by rho on both sides. And in this m by rho, what is m? M is molecular weight and rho is density of material of dielectric material. So now if I multiply on both sides, then we end up having it as m by rho into epsilon r minus 1 by epsilon r plus 2 is equal to n. Of course, here I have m by rho into n alpha by 3 epsilon naught. But what we are going to observe here is, if I take this mn by rho, if I consider this one, this is epsilon naught, and I am taking this expression mn by rho. What is this mn by rho? M is molecular weight, N is number of atoms or molecules per unit volume, and rho is density, and this particular value is nothing but Na. And what is our Na? Na, it is called Avogadro's number. So what is our Na? Na, it is called Avogadro's number. And what is the value of Avogadro's number? So this Avogadro's number is, of course, we have some 6.023 into 10 to the power of 23 atoms or molecules per mole. Okay, if you want to take per kilomole, so atoms or molecules per mole of a material, or 10 to the power of 26 atoms or molecules per kilomole. So this is our Avogadro's number. And if I substitute this Avogadro's number in our expression, so what we have on the left hand side, m by rho epsilon r minus 1 by epsilon r plus 2. So our right hand side, it will become Na alpha by 3 epsilon naught. Now once I get it, this whole expression, I'll replace it with Pm. Okay, so this whole expression, I'll write it as m by rho into epsilon r minus 1 by epsilon r plus 2. So this is equal to Pm. This is another form of Clausius-Mosotti equation. So as you can see, this particular equation, m by rho epsilon r minus 1 by epsilon r plus 2, which is equal to Pm, it is another form of Clausius-Mosotti equation. And if you look at this form, what is our Pm? What is Pm here? Where Pm? It is called as molar polarization. So this Pm, it is called as molar polarization. And how this molar polarization is given? It is given as Na alpha by 3 epsilon naught, where Na is Avogadro's number, alpha is polarizability, and of course epsilon naught is permittivity of free space. And what is the value of permittivity of free space? It is taken as 8.854 into 10 to the power of minus 12 farad. So as you can see, this expression, okay, this expression is a very important expression. So this is one form of Clausius-Mosotti equation. And then we have one more expression. This is another form of Clausius-Mosotti equation. So as I told you, this equation is very useful. So it will help us to find micro or macroscopic quantity once we know the other opposite type of quantity related to a dielectric material. And for this, of course, we have considered first by taking into consideration microscopic property, which is polarization. We try to get it in terms of microscopic, which is polarizability. And this formula, it is used in many applications, usually numerical problems. So here we have taken into consideration, of course, induced dipole moment as well as internal local field. And why we have to consider internal or local field? Because this field, this total electric field, due to microscopic field contribution as well as microscopic field contribution. So because we are trying to get that relation in terms of microscopic, so that's why we have to take care of, like we have to take help of internal field or local field. So I hope you are able to understand this derivation part of Clausius-Mosotti equation, which is very important equation for a dielectric material. So with this, I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.